Hello everyone, I'm Zeyu Yan from University of Maryland. I'm excited to introduce you to our work FabHydro, printing interactive hydraulic devices with an affordable SLA 3D printer. Printing integrated functional artifacts has been discussed since Maker 3D printers are released. Aside from the tremendous amount of complex topologies and assemblies created by the huge Maker community, we have also seen researchers develop fabrication systems and methods around existing hardware and electronics to make smart functional products. Some takes advantages of existing fabrication tools such as 3D printers and laser cutters and modify them to produce interactive items. Many other researchers also came up with brilliant ideas to use smart material or engineer special structures to fabricate interactive artifacts. In a similar vein, we present you FabHydro, a set of rapid and low-cost methods to prototype interactive hydraulic devices based on an off-the-shelf 3D printer and flexible photosensitive resin. Note that a couple of years back, the work of Printable Hydraulics has explored ways of printing actuatable hydraulic devices with 3D printers. They presented the idea of printing fully functional hydraulic device directly off the printer intriguingly and thoroughly. As a step forward, our work utilizes a low-cost printing method, stereolithography, which has been widely used in the HCI community and is 1,000 times cheaper than the industrial inkjet printer used back then. Correspondingly, we introduce a series of technology contributions that are unique to SLA printing, such as overcoming the instability of printing flexible material and embedding liquid inside prints using SLA. Finally, we present a systematic design space for printable hydraulic devices, aiming to support designers to quickly make and customize hydraulic-driven mechanical prototypes, which we believe will open the opportunity for the HCI and the Maker community to this technology. Following, I'll introduce some key details of FabHydro, including our printing process, our design space, and a set of applications to show how each modular design in the design space features in hydraulic systems and various use cases of interactive hydraulic devices. A conventional hydraulic device usually consists of a generator, which output hydraulic fluid out into the system, a set of transmitter, mainly valves and tubes that direct fluid towards the actuator, which behaves as an end factor. Given this definition, to print a hydraulic device, we need two things to be sorted out. One is to make sure the generators are deformable as an output reservoir, and the actuator should also be deformable to pursue shape changing. And two is to make sure that the entire system is sealed with liquid inside. Let me talk about it one by one. We do want to make sure things are deformable to ensure the actuation, but in the meantime to be durable and stiff enough to hold the structure from rupture. So we followed the Shore value, which is a parameter to show material flexibility, and experimented with three of the most representative resins off the shelf. The regular resin, which we use the most in daily printing, are obviously not flexible enough to make desired deformation before fracture under load. The impact-resistant resin are able to deform a lot under load and recover. However, the speed of deformation and recover is as slow as him. Then, we found F39, F69 series that deforms well, recovers fast, and still remains rigid when just enough of thickness is in presence. The flexibility of the material is what we want to see, but it is also causing problem during printing thin overhangs and elongatable structures. In the SLA printing process, the parts are lifted upside down and printed between the base plate and a thin foil, called FEP. At the end of curing each layer, the plate will pull parts from the FEP and send it back to a height that is one layer thickness above the FEP to print the next layer, which we call demolding. When this is happening, thin overhangs will flex in the liquid resin and won't cooperate and stay with the FEP at the right height. So in short, we adjust the setting of the support generator to make sure the edges and corners of the overhang are anchored properly to the base plate. Another thing that could happen during demolding is that the part, since it's printed with flexible resin, will elongate instead of detach from the FEP, causing the next layer and the layer from then on have no space to grow underneath the existing parts. To solve this, we made multiple trials and simulations, and a customized panel-shaped support could finally solve this problem. As shown in the simulation result, the deformation with and without panel support comparing to the original state, which is shown on the left-hand side, has a huge difference. and printing experiments shows consistency with this result. Now that we know we're able to print the shell structures of the hydraulic system, it's time to seal the liquid in it. We propose two methods to accomplish that, and each has its advantage depending on user's need. First of them is called submerged printing. In this method, we customize the printer with an extended displacement from the original print bed paired with a raised resin bed. We're following the same logic of conventional SLA process, except for print bed is always lowered into the liquid resin, even when the demolding is happening. This will guarantee that the parts are fully submerged in the resin liquid, which inherently seals the uncured resin inside if the 3D model has a chamber topology when modeled. The second is called print with plug. To introduce more versatility to the end product, we came up with a threaded plug and drain hole pair design utilizing the inherent accuracy given by the SLA process, so that the user can design the model, 3D print it with a modified machine, and add fluid to it, and stuff the drain hole or drain holes depending on the design to lock the liquid inside the product. Putting the two methods together, the submerged printing requires a simple modify to the printer, but can print hydraulic devices usable directly off the printer, so it's suitable for fast prototyping and iterations for researchers and designers. The print with plug allows more versatility in terms of hydraulic fluid use in the system. Despite of having to introduce transmission fluid manually, users don't have to worry about modifying the printer as well as the slight chance of part rupturing and reveals the uncured resin in the end product. It's also more suitable for users who needs a modular design in the system and need to swap out parts from time to time. Also, it will adapt to bigger models better since users can divide them into smaller sections and join them together after printing. Now that we know we can print parts with deformation and locked-in liquid, how do we construct end-to-end hydraulic devices? As we mentioned, hydraulic devices are constructed mainly with three sub-modules: generator, transmitter, and actuator. We constructed a design space following this, each with design guidelines and suggested parameters. Generators are designed with bellows structures acting as a reservoir and pump in the system. The bellows structure is adopted to maximize the output pressure and volume into the system. It comes with flexible sizes and flexible sectional shapes to suit users' need. And if needed, it could also be motorized with remote control. After energy is pumped out from the generator, it transmits in the system with tubes and transmission is controlled with valves. Tubes can be printed in any direction as long as the inner diameter is bigger than the lower bound, which varies between printers, and the length is usually limited by the print volume of the printer. Our printer were able to print tubes with minimal inner diameter of 3 mm with a maximum length of 4.18 meters. Our system also features a switch for users to decide whether to cut off the transmission either in the passive state or the actuated state. The switch is a twisting knob with thread that threads in to block the transmitting channel and threads out to let through. Our actuator design is based on expansion units. With tailored design parameters, when pressure increases in the actuator, each compartment will expand and squeeze each other apart to make global shape change. With expansion compartments distributed in different ways, our system can pursue bending, straightening, expanding, and curling. And if these 1D actuators are concatenated together in different ways, more complex actuation can be achieved. Now that we have all the tools we need, the printer, the printing method, and the modular design, now let me showcase some applications. In this example, we show a portable folding lamp with adjustable posters. The lamp is printed one-off using a submerged printing technique. When the user presses the generator, the lamp will unfold and light up. The user can adjust the amount of folding by pressing the generator to different heights. An LED is attached to the lamp with copper tapes, which close the circuit when actuation happens. One of the benefits of hydraulic devices is that the force applied at the remote place can be transmitted with minimal loss. To demonstrate this, we designed a robotic gripper with tactile control that potentially allow handling hazardous material from a distance. In this example, we augment a fluffy toy with controllable motions. We include a printed switch to enable binary controls of the elephant's action. Two straightening actuators are used to activate the arms of the elephant, and one bending actuator is printed to control the trunk. The user can choose to actuate all 3 actuators at once or actuate them individually by turning the switch on and off. In this example, we demonstrate a collaborative game with printed tangibles. 2 gamers each will control a push-button generator with a custom shape of a cat paw. The height change of the 2 buttons will jointly decide a tangible prob's location on a touchscreen, of which the fishing game is displayed. The tangible prob is designed with a shared connection to 2 parallel extending actuators, and each actuator is then connected to 1 cat paw generator. The game's goal is for the 2 users to catch fish by placing the fish prompt at the correct location collaboratively. So far, we have seen what FabHydro can do as a fabrication method for hydraulic devices with affordable SLA printers. Moving forward, we aim to embrace the full potential of FabHydro with the Designer Toolkit. As a start point, we implemented a panel support generator and a preview of the deformation with FEA simulation in Rhino Grasshopper. In the future, we will include parametric design features that allow designers to quickly connect different hydraulic components and add real-time simulations of the actuation result. In all, FabHydro is a rapid low-cost method to print hydraulic devices with an off-the-shelf SLA 3D printer. Features 2 printing methods and a systematic design space. With the low-cost setup and accessible workflow, we hope our work can further enrich the design for 3D printed interactive devices and complement the current design toolkit for the HCI community. Thanks for listening.